Bismillahirrahmanirrahim. I'm Amal Suhail and my roll number is 21TE04. Today I'm going to implement the first lab of digital signal processing. In this session, I'll be implementing MATLAB codes to explore various concepts in digital signal processing by creating various functions to visualize signals through plotting. I observe the outputs of the implemented codes in MATLAB. The objectives of this lab is to explain the importance of digital data in the context of sort, search, store, and transmit, how to plot different signals, writing scripts in MATLAB or Octave, and creating and calling different functions in MATLAB. In the context of digital signal processing, elucidate the essence and intricacies encapsulated within the term digital. In the realm of digital signal processing (DSP), the term digital refers to the representation and manipulation of signals in a discrete, quantized form. The essence of digital in DSP encompasses several key aspects. Discrete representation. Digital signals are represented as a sequence of finite values. This discrete representation allows for efficient storage, transmission, and processing of signals using digital systems. Quantization. In the digital domain, the continuous amplitude values of analog signals are approximated to a finite set of discrete levels. This process is known as quantization. The precision of quantization is determined by the number of bits used to represent each sample. Sampling. Digital signals are obtained through the process of sampling, where the continuous analog signal is measured at regular intervals. The rate at which these samples are taken is known as the sampling frequency. The Nyquist theorem dictates that the sampling frequency must be at least twice the maximum frequency present in the signal to avoid aliasing. Processing with algorithms. Digital signals can be processed using algorithms implemented in software or hardware. These algorithms can perform various operations such as filtering, convolution, Fourier analysis, and many more. Signal storage and transmission. Digital signals can be easily stored in digital memory devices and transmitted over digital communication channels. This enables robustness against noise and interference as well as facilitates error detection and correction techniques. Task 2 of the lab is explain how does the choice between linear search and binary search in DSP applications illustrates the relationship between digital data and sorting and what are the implications for data processing efficiency. Linear search, nature. In a linear search, data is examined sequentially, one element at a time, until a match is found or the entire dataset is traversed. Implications. Linear search is straightforward and suitable when the data is not sorted. Its time complexity is O of n, meaning the time taken to search grows linearly with the size of the data set. Binary search. Nature. Binary search is applicable when the data is sorted. It involves repeatedly dividing the search interval in half, comparing the middle element to the target value, and narrowing down the search until the element is found. Implications. Binary search has a time complexity of O log n, which is significantly more efficient than linear search for large datasets. This efficiency is particularly crucial in DSP applications where real-time processing and rapid data retrieval are often required. Relationship between digital data and sorting. Unsorted data. Digital data in DSP applications is often represented in a discrete quantized form. Sorting in this context refers to the organizing the data in a specific order. If the data is unsorted or the order is not crucial, a linear search may be sufficient. For example, when processing time series data or analyzing signals, the order of samples may not inherently matter. Sorted data. If the data is sorted, binary search becomes a more efficient choice. Sorting is a common pre-processing step in DSP, and binary search can take advantage of the ordered structure, reducing the search time logarithmically. Implications for data processing efficiency. The choice between linear and binary search directly impacts the efficiency of data processing in DSP applications. For unsorted data or situations where the cost of sorting is high, a linear search might be more practical. When dealing with sorted data, the use of binary search improves efficiency significantly. The logarithmic time complexity ensures faster search times, making it suitable for real-time processing in applications where computational sources are limited. Here is the task 3 of the lab. In the domain of digital data, what strategies and techniques can be employed to enhance data transmission efficiency? In the domain of digital data, several strategies and techniques can be employed to enhance data transmission efficiency. These approaches focus on optimizing the use of available resources, minimizing errors, and ensuring reliable and swift transmission. Here are some key strategies. Compression. Compression reduces the size of data before transmission, thereby decreasing the required bandwidth and transmission time. Error detection and correction. Implementing error detection and correction techniques ensures data integrity during transmission, reducing the likelihood of errors and need for retransmissions. Multiplexing. Multiplexing allows multiple signals or streams of data to be transmitted over a single channel simultaneously, increasing the overall efficiency of data transmission. Modulation and coding. Modulation changes the characteristics of the carrier signal to encode digital information, and coding schemes improve the robustness of data transmission. Protocol efficiency. Choosing efficient communication protocols reduces overhead and improves the overall efficiency of data transmission. Then comes parallel transmission. Transmitting data in parallel over multiple channels or paths increases the overall data throughput. Dynamic bandwidth allocation. Dynamically allocating bandwidth based on the current network load optimizes resource utilization. By combining these strategies and techniques, data transmission efficiency in the digital domain can be significantly improved. Here is the task 4 of Digital Signal Processing Lab 1, which is about plotting sinusoid. CLC command is used to clear the command window. Clear wars command is used to clear all the variables from the MATLAB workspace. Close all command closes all the existing figures in MATLAB. T is the time vector that ranges from 0 to 1 with a step size of 0.01, which means it generates the values between 0 and 1 with an increment of 0.01. F is equals to 1 is the frequency of the signal which we are going to implement, and it is set to 1 Hz. Signal is equals to sine 2 by ft. The sinusoidal signal is represented by a sine function and is defined as sine 2 by ft, where f is the frequency. 2 pi is used to convert this frequency into angular frequency, and t is the time vector defined above. The plot function is used to create a 2D plot of the signal against time. Time is represented on the x-axis, whereas the sinusoidal signal is generated on the y-axis. Let us observe the output of this code. Here we can observe the sine smooth curve of a sine wave that starts from 0, reaches its maximum amplitude at 1, again returns to 0, reaches its negative amplitude at -1 and returns to 0 again. So this code basically generates a sinusoidal signal of 1 Hz and plots it against time with an interval of 0 to 1 with a step size of 0.01. The resulting plot represents one complete cycle of the sine wave. Now let us observe the effect of changing the frequency of the signal. For example, if we set the frequency to 5 Hz, we can observe that increasing the frequency to a higher value, the signal will oscillate more rapidly, which means it completes more cycles within the specified time interval. And if we decrease the frequency, the signal will oscillate more slowly. So it represents the inverse relationship between the frequency and time period. Task 5 is the continuation of task 4. In this code, we just added title, labels, and access bound to the signal graph. Title command adds the title to the plot, providing information about the content of the plot. In this case, the title is Plot of Sine Wave 1 Hz. Y-label command labels the y-axis with the text amplitude, providing information about the quantity represented on the y-axis. Xlabel command is used to label the x-axis with the text time in seconds, providing information about the quantity represented on the x-axis. Axis command is used to bound the axis to certain limits of the plot. This represents x minimum, x maximum, y minimum, and y maximum. In this case, the x-axis limits are set from minus 0.5 to 1.5 and y-axis limits are set from minus 1.5 to 1.5. This can be useful to control the displayed range of the plot. Let us observe the output of this code. Here we can observe that x-axis is labeled as time in seconds, whereas y-axis is labeled as amplitude, and title of the plot is plot of sine wave 1 Hz. X-axis limits are bound from minus 0.5 to 1.5 and y-axis limits are bound from minus 1.5 to 1.5. Sixth class is about plotting multiple signals in the same figure. CLC, clear words and close all command clears the command window, clears all the variables from the MATLAB workspace, and closes all the existing figures in MATLAB. T is the time vector that ranges from 0 to 10 with a step size or an increment of 0.01. The frequency of the first sinusoidal signal is set to 10 Hz, whereas the frequency of second sinusoidal signal is set to 20 Hz. This line generates the first sinusoidal signal using the sine function, and signal 2 generates the second sinusoidal function using sine function. Plot command plots both the signals in the same figure. The time vector is on the x-axis and signal 1 and signal 2 are on the y-axis. The title command adds the title to the plot. In this case, the title is plotting multiple signals in the same figure. Y-axis is labeled as amplitudes and x-axis is labeled as time in seconds. Axis command is used to set the axis limits for the plot to show only a portion of the signals for better visualization. The x-axis limits are set from 0 to 1, whereas the y-axis limits are set from minus 1 to 1. Let us observe the output of this code. Here we can see the plot containing both the signals with different frequencies. Task 7 is about plotting multiple signals in one figure without connecting dots. This code generates two sinusoidal signals, signal 1 with a frequency of 10 Hz and signal 2 with a frequency of 20 Hz, plots them in the same figure without connecting the dots. It plays the sound corresponding to the signal 2 at the sampling rate of 16,000 Hz. And it adds titles, labels, and axis limits for better visualization. The hold on command activates the hold on mode, allowing multiple plots to be added to the same figure without clearing the existing content, whereas the hold off command turns off the hold on mode, preventing further plots from being added to the current figure. Let us observe the output, and we can hear, as we can observe, the red and blue dots. The red dot represents the frequency, sinusoidal signal with a frequency of 20 Hz, whereas blue dot represents the sinusoidal signal with the frequency of 10 Hz. We heard a beep sound corresponding to the second signal, and the title of the plot is plotting without connecting multiple dots, and y-axis is labeled with amplitudes and x-axis is labeled as time in seconds. Task 8 is about generating random data from a uniform distribution. N is equals to 50 represents the number of data points to be generated. R is equals to rand n1. This line generates n random numbers from a uniform distribution between 0 and 1 and stores them in the column vector R. Plot R command plots the generated random data R on the y-axis against the index of each data point on the x-axis. M is equals to mean of R. This line calculates the mean of the generated data R and stores it in the variable M. The hold on command is used to create multiple plots on the same figure. This plot command activates or displays a horizontal line representing the mean value M across the entire x-axis. The title command displays the title of the entire figure or entire plot on the graph. Let us observe the output of this graph. As we can see, the random data is represented by blue variations of the values, and mean is represented by the constant line on the horizontal x-axis. Task 9 is about creating a MyMin function that displays minimum value as a result. This line creates a MATLAB function named MyMin. It takes one input argument named vector. The function will return a value which is stored in the variable min value. If the input is not a vector, it generates an error message, and if the input is a vector which represents that it is a valid vector, then this line uses the min function find the minimum value in the vector. The minimum value is then assigned to the variable min value. It marks the end of the mymin function. Now, to call the mymin function, this line prompts the user to enter a vector, and the entered vector is stored in the variable myVector. It calls the minimum function named as mymin function with myVector as the input and stores the result in minimum value. The display command is used to display the minimum value in the command window. Now let us observe the output of this code. Here it is asked from the user to enter the data or enter a vector. Now, for example, if we enter 0, 1, -1, -2, and 10. The minimum value is -2. Here we can observe that the minimum value is obtained as a result of the input vector, which is a valid vector. Task 10 is about creating mymax function and displaying the maximum value in the result. This line is used to declare a MATLAB function named mymax. It takes one input argument vector. The function will return a value which is stored in the variable max value. If the input vector is not a valid vector, it generates an error message which includes input must be a vector. If the input vector is a valid vector, this line uses the max function to find the maximum value of the vector. The maximum value is then assigned to the variable max value. It marks the end of the mymax function. Now to call the mymax function, the code is written as myVector is equal to input enter a vector prompts the user to enter a vector, and then entered vector is stored in the variable myVector. This line calls the mymax function with myVector as the input and stores the result in the maximum value. And display command is used to display the maximum value in the command window. Let us test this code. Firstly, we have to write the valid vector, which is 0, 6, 8, 12, -1. The maximum value is 12. Here we can see that in the above vector, the maximum value is 12, so the output is 12. This MATLAB code defines a function called myAverage and then calls this function to calculate and display the average value of a user input vector. For example, if we write the code like 0, 6, 4, 3, 2, the average value is 3. The average is calculated by adding all the components of the vector and dividing it by total length of the vector. So the average value of this vector is 3. Lab task 12 is about creating a mysort function. So this line declares a MATLAB function called mysort. It takes one input argument named input vector. The function returns the value that is stored in the variable sorted vector. Now, if the vector is a valid vector, it uses the sort function and returns the value, and return value is stored in the sorted vector variable. It marks the end of the sort function. Then mysort function is called and the result is stored in sorted vector variable. As a result, the original vector and sorted vector are displayed in the command window. Now to test this code, enter a vector named original vector 0, 1, 4, 7, 9, 3, 5. The original vector is 0, 1, 4, 7, 9, 3, 5, and the obtained sorted vector is 0, 1, 3, 4, 5, 7, 9. Task 13 of the DSP Lab is about myReverse function. Firstly, it declares a function named myReverse. It takes an input argument named input vector. The function will return a value which is stored in the variable reversed vector. And if the input is a valid vector, this line uses the flip function to obtain a reversed version of the vector. Now we will observe the output of this code by calling the myReverse function. Let us enter a valid vector 0, 1, 2, 3, 4, 5. We press enter. Original vector is 0, 1, 2, 3, 4, 5, and by calling the myReverse function, the reversed vector is obtained as 5, 4, 3, 2, 1, and 0. This is the task 14 of DSP Lab, which is about drawing multiple plots in one figure using subplot function. Let us observe the output of this code. Here is the output. The random signal is plotted at the first index of 1 cross 2 matrix, and the sinusoidal signal is plotted against second index of the 1 cross 2 matrix. It is the last task of DSP Lab 1, which declares a function named win4. The time vector is defined from 0 to 10 with a step size of 0.01. It means that it generates the values from 0 to 10 with an increment of 0.01. There are 4 function values. The first one is sine function, the second one is cosine function, the third is sawtooth function, and the fourth one is an exponential function. This code uses the subplot function to create a 2 cross 2 matrix, and it sequentially plots each function in its designated subplot. Titles are added to each subplot indicating the corresponding function being plotted. Finally, the sgTitle function is used to provide an overall title to the entire figure summarizing the content of the subplots. The resulting figure provides a visual comparison of 4 different functions over the specified time range. So to observe this, let us run the output. As we can see, the 4 signals are plotted into 2 cross 2 grid: the sine function, the cosine function, the sawtooth function, and the exponential function. So to conclude, I would like to say that these tasks provide a hands-on introduction to MATLAB basics, including function creation, vector manipulation, plotting, and user interaction.